That means when I generate the sound, and then it takes infinity time to be reduced by 60 dB, right? Oh, that's a perfectly reverberant room. That means if you go to the room that is enclosed by rigid surface, and that does not have any damping, and also you are exciting the air that does not have any damping. That is very challenging. Can you make an air that does not have any damping? That belongs to the physicist, not engineer, right? Yeah, that may be very challenging. Let's make air that does not have any damping. That means if I use that kind of air in a tube, then I can send my voice to my girlfriend in the United States, right? Hello, then. Just take a long time to go there, compare with the cell phone or whatever we are using, she can hear, right? So no problem, right? And then she, okay, I'm doing fine, then takes a long time. So you maybe take a one nap to listen what she will talk to you, but anyway you can hear. Okay. Let me ask you, what would be the room that has a reverberation period of 0? That means when I shout, it takes only instantly it decays 60 dB. Right? That means I have either 0 volume, no. Either 0 volume, that is a trivial case, or infinite open area. That means I'm standing on the field that is open, right? So that is two extreme case. In between, there will be a Catholic church or lecture hall or our first floor, where we often have a Friday concert or Thursday concert. So what about the reverberation period of this room? Or I would ask, what would be appropriate reverberation period appropriate for lecture hall? That will be about 1.0. Okay? 1.0. That is fantastic, right? What would be appropriate reverberation period to listen chamber music? You will have a very nice chamber music this coming Thursday. Today, on our auditorium, starting at 7 o'clock in the p.m., Vivaldi, okay? I suggest you go over there because there will be a good, they will explain every history behind of the Vivaldis. So that will be fantastic. So for chamber music, in the literature, they said it's good for 1.2, 1.5. Okay, that means we have a list of reverberation period that matches to certain music or acoustical environment. If someone asks you, can you design this room or can you convert this room that will be appropriate for lecture hall, then what you can do is, because the volume is you cannot change, you can change the open area window, therefore you can either block the window or larger window, that will do. But open area window it does not have to be real window, right? Open area window is something that can absorb energy from inside. So we can write AS absorption coefficient. What is the absorption coefficient? What is the absorption coefficient? How much energy is absorbed? So absorption coefficient is usually defined as energy in and energy observed. Right? In the text, you can find that there are various ways to measure the absorption coefficient. Okay, one way would be put inside of the room the material that want to you measured absorption coefficient, like polyethylene material, or in Korean, sponge. Okay? And you put that material, sound absorbing material, inside the rigid, enclosure that is surrounded by rigid boundary, and assuming that the sound absorbed by the air is much smaller than sound absorbed by the absorption material. And what you do is you put the microphone over here and the speaker over here and generate the sound, okay, and generate the sound and then turn off the sound, okay? And then you measure E, and how you measure the observed? It's easy. Energy will be proportional to that is kinetic energy, and the potential energy would be right? If it is plane wave, then and we can find out. Now you can measure E in the beginning, that is EI, and then you measure E when sound is down to, for example, 60 dB, then you can measure the observed, and then you define R per I. Using this kind of technique, we call the measuring the absorption coefficient in the reverberation room.